Okay, let's talk work. So remember from either Calculus 2 or your physics classes that if you want, here's my picture, I'm dragging a wagon from point P to point Q with a certain amount of force. Let's pretend for a second the force is in the direction of motion, parallel to PQ. Then what's the formula, if you were to write it out using words, what's the formula for work? Force times distance. And you all studied that in Calc 2, among other places. Force, and that's regular multiplication, force as like a real number times distance as a real number. Does that seem reasonable? Now, the problem is, as the picture indicates, I'm applying the force not in the direction of motion. It's like this force vector coincides with the handle, right? It's not the same length as the handle because the force will be different than the displacement vector represented by the handle, or that represents the handle. But it's parallel to it. It coincides with it. It's not in the direction of motion because the wagon's moving just on the ground from point P to point Q. So whatever this value is, it's not the magnitude of F, the force vector, unless you made F horizontal or parallel to PQ if it's not horizontal. Okay? So that's a problem, right? Well, we'll fix the problem pretty quick. So let's talk about some notational issues. The projection of F onto PQ, that's what this notation stands for down here. Projection. Well, you know what, I'll just write it here. Projection of F, the force vector, onto the displacement vector PQ. In words, that's what that notation means. Proj F and then subscript PQ. Or proj subscript PQ and then F. What does that represent up here in my picture? Well, imagine putting a copy of PQ here. So this is vector PQ. Then imagine the sun is shining and it's a beautiful day. It's not today, but imagine it. It's right above, and it's shining straight down. Then the projection of F onto PQ is the shadow. So if you project this tip straight down, so that dotted line segment is orthogonal or perpendicular to PQ, then the vector in blue is the projection of F onto PQ. That makes sense? Okay, then getting back to work, work is force times distance, right? Another way then to think of the projection of F onto PQ, since F is a force vector, is it's the force exerted in the direction of PQ. It's the amount of this vector F, this force vector, in the direction of PQ. And that's what we need in our formula up here, magnitude-wise. That's what we need in our formula up here to create a proper work formula. So a way to rewrite work in terms of the projection of F onto PQ, well, we're going to use the magnitude of that, because remember, the work is actually a scalar. So then let's change it to, okay, let's look at the formula for work. That must be the magnitude of the projection of F onto PQ times, well, okay, PQ distance-wise would be the magnitude of PQ, right? The length of PQ would be the magnitude of PQ. So that's the distance. Okay, so that's just saying in symbols what we said above. Work is equal to force in the direction of motion times the distance that you're moving that object. Do you agree with that symbolically? So what we would like to do is come up with a formula that we can actually use to compute work based on the symbolism. The good news here is we can use good old trigonometry. So, okay, let me just take this as a triangle. So, but now let me think of that force vector and just in terms of its length, so magnitude F, right? So forget about the arrows. Let's think about a triangle here. And then this guy projected down would be that guy. Make it solid. And then this projection F onto PQ, this guy. This guy would be theta. I didn't label it over there, right? But that would be theta. The angle between F and PQ, or projection of F onto PQ, either one. So, is there a trig formula for getting the length of the adjacent side if you know the angle and the hypotenuse, the length of the hypotenuse? Goes back to the CAH, copart, or SOHCAHTOA, if you know what that acronym stands for. Cosine equals adjacent over hypotenuse, but you gotta solve for adjacent. So magnitude of F, the hypotenuse, times the cosine of theta. Isn't that the length of this side in blue? In other words, the length of the projection of F onto PQ. The projection of F onto PQ is a vector, make no mistake. So we're finding its length. That seem reasonable to you? So what? Well, I'm going to put that result right in here. So it's the magnitude of F times the cosine of theta times magnitude PQ. That's a work formula. Another way to write that would be, it's all of these factors are just regular real numbers, regular multiplication. So I'm going to rearrange the multiplication and make it magnitude F, magnitude PQ, times the cosine of theta. That's just commutative property of multiplication. And that's a formula you can use if you know the angle that the handle of the wagon is at, or whatever you're using to drag the object. If you know that angle, and you know the amount of force applied, that's the magnitude of F, and you know the distance, PQ, that you're traveling, you can use that formula. There's another formula that pops out of here right away, though. Using the alternate form of the dot product, what is magnitude F, magnitude PQ, times cosine of theta? It's F dotted. Now, F dotted with PQ. Now, this is a moment for mathematical appreciation. Why do mathematicians get all giddy now? What does that look like? Doesn't it look like the original formula, except it's a dot product of two vectors? Force times distance, doesn't it kind of look like that? Force times distance, we're talking about multiplying scalars together, but now we're talking about multiplying vectors, but the formulas kind of look the same. All right, and then down here, this is a summary of all three of those, right? Now, the units of work are created by taking the units of force times the units of distance, or sometimes we turn them around. So the foot-pound, if you're using English units, right? Pound-foot, I suppose, but we use foot-pound. Or the Newton-meter, but the Newton-meter is also known as a joule. 1 Newton meter is 1 joule. Okay? Pretty much standard. I mean, you could be in inch pounds. That's acceptable. But if you're using metric units, it's going to be Newton meters or joules.